Hello, everyone. Good afternoon, or good morning, or good evening, depending on where you are. Thanks for joining us today, giving us a few minutes of your time. My name is Jeff Prosise. I work at Wintellect. Much of what I do these days in terms of doing software development involves machine learning and AI. And we put this webinar together because we thought other people might be interested in learning a little bit about ML and AI as well. I've got my email address up there, also my Twitter handle if you want to tweet. If you have any questions or something after all this is over, feel free to shoot me an email and I'll see if I can help you out. So I have a lot of stuff to cover here. I'm going to have to cover it quickly, and at the end I'm going to give you a URL to a public repo I maintain on GitHub where you can download a bunch of code samples, all the ones that I'm going to show, as well as some that I won't be showing either. But my goal here is, assuming you are a software developer, to give you a working introduction to machine learning, not only what it is and how you build machine learning models, but also what you can do with machine learning, and perhaps just as importantly, what sorts of things you can't do with machine learning. Now, I should say at the outset, my goal isn't to turn you into a data science. My goal is to turn you as a software developer into a developer who is more knowledgeable about ML and AI, how you might use it to build smarter and better software than you did just a few years ago. Sometimes I describe the relationship between a data scientist and a developer who is knowledgeable about ML and AI to an engineer and a physicist. Physicists think the great thoughts, make the new discoveries, figure out how the universe works. But an engineer's job is to apply what the physicists have learned to solve real world problems, to solve business problems. And it's the same way here. The world needs data scientists who come up with new neural network architectures and all of that. But the world also needs software developers who understand how to take what the data scientists have invented and apply it to solve business problems. And that is the thrust of what I want to communicate to you today. I want to start by showing you some numbers, a very simple table of zeros and ones. And this table is small enough that you and I can look at it and we can come up with a set of rules for predicting what the outcome should be in any given row. In other words, for a given row, what should the value in red in the rightmost column be? It looks like that outcome, that value in the right-hand column, should be a 0 if there are more zeros than ones in the row to the left of it, or should be a 1 if there are more ones than zeros. So you and I can look at this pretty quickly, figure out that we should fill in a 1 in that missing square at the lower right. But let me make it a little bit harder. Suppose that table of zeros and ones were just a little bit bigger. In fact, imagine it's even bigger than this. Imagine that there are hundreds of thousands or even millions of rows of zeros and ones. And imagine that instead of 30 or 40 columns, there are thousands or even tens of thousands of columns. Both of those are very common in machine learning. We often throw at machine learning data sets that contain thousands or tens of thousands of columns and millions of rows. Now, in this example, what we want to do is the same thing we did in the previous one. Find patterns in these zeros and ones so that we can predict an outcome on the right. In this case, what value should I fill in for that red box in the lower right corner? Should it be a 0 or a 1? Well, just because of the volume of information, it's much, much harder to look at this and find patterns that would tell us whether that should be a 0 or 1. In fact, you can't get the right answer just by counting the zeros or ones in a column. It's much more complex than that. And again, it's only even more complex if there are thousands of columns and millions of rows. The reason I want to show you this is exactly what machine learning does. Forget the math, forget the equations that you might have seen when you do research online. What machine learning is fundamentally about is looking at large data sets containing numbers, could be zeros and ones, could be something else, and finding patterns in those numbers that allow it to predict outcomes. We often say that machine learning is used to do predictive analytics. And when we say that, that's exactly what we mean. We're going to let machine learning look at a data set, find the patterns, find the algorithms that will allow it to fill in the missing blanks, and then we'll use it to make future predictions from the input that we provided. Now, I'm not simplifying matters too much when I say machine learning is really about finding patterns in numbers or patterns in zeros and ones. One of the examples I'm going to show you today is how to do sentiment analysis on text, how to look at arbitrary text that might come from a tweet or might come from a Facebook post or something else, and grade it from 0 to 1 on whether that sentiment is negative or positive. I'm also going to show you how we use machine learning to do cutting edge spam detection. Those models aren't too difficult to build once you have the data. And in both of those cases, what we're going to end up doing is build a data set that consists of zeros and ones. There will be one row in this data set for every email that we train the model with, or every piece of text we train it with, so the model can predict negative or positive sentiment. And there will be one column in the data set for every word in the emails or the tweets or whatever body of text we trained the model with. Now, typically, there are 10 to 40,000 columns in this data set because there are something like 50,000 commonly used words in the English language. You can imagine if there's a corpus of email, for example, large enough, it might cover a significant percentage of those. And sometimes we train models like this with hundreds of thousands or even millions of emails or other pieces of text. At the end of the day, what we're building is a big table of zeros and ones. It's mostly zeros, by the way, but in a given row, there's a 1 in a column where the corresponding word appears in that email or piece of text we're training with. Again, you and I would be hard pressed to look at all these zeros and ones and find patterns, but this is what machine learning excels at. And by the way, it's not always just zeros and ones. Another problem that has been solved very well by machine learning today is classifying images. We refer to these generically as computer vision tasks. Looking at a photo, for example, and finding the faces in the photo, identifying the faces in the photo, identifying objects in the photo, or even looking at a photo and saying, does this photo contain a dog or a cat, or does it contain neither? In machine learning, all of those are called image classification tasks. And at the end of the day, here's how they work. I took this example from one that I'll show you time permitting towards the end of this presentation, where we're going to train a machine learning model with a bunch of facial images of famous people, a couple of hundred, well, about 100 or more photos each of 5 people. And then we're going to ask the model to take a face as input and tell us as accurately as it can whose face that belongs to, or what person that face belongs to. The model itself looks like this. There's one row for every image that we train the model with. There's one column for each pixel in the image. So if these are 100 by 100 photos, which are not that large, even if they're monochromatic, that means we have 10,000 columns in this data set. Here, we're not dealing exclusively with zeros and ones. If these are grayscale images or even RGB images in each channel, we'll be dealing with values from 0 to 255. And on the right-hand side, those numbers on the right identify which person the face belongs to. Once more, we're dealing with a very large data set of numbers, lots and lots of rows, thousands, even tens of thousands of columns. But we can do facial recognition this way because machine learning, again, is very good at looking at all those numbers and finding the patterns that allow us to feed another row in and have it tell us what the outcome should be. So I hope that makes it clear what machine learning is without going into math and equations and things like that. Intuitively, that's what it's about. Now, let me set the stage a little bit for some of the things that we're going to talk about in this session. This is what the landscape of artificial intelligence, or AI, and machine learning looks like today. Technically, machine learning is a subset of AI. But within machine learning, there's a subset called deep learning. Now, confusingly, when most people talk about AI today, they're not talking about AI in general. They're talking about deep learning. Deep learning mostly relies on neural networks to work the magic of doing image classification or image generation and things like that. I'll do a separate webinar later specifically on deep learning and neural networks and what they are and how you build them, what libraries are available, things like that. But for today, we're going to focus on the brown oval, machine learning, excluding the deep learning subset. In other words, we're going to be looking at classical, sometimes called statistical machine learning models, support vector machines, models that use naive Bayes as a learning algorithm, or logistic regression, or what have you, so that we can sort of see what kinds of problems we can solve with those models and how we go about solving them. One way to think about machine learning is in terms of what you and I do as programmers. Typically, as programmers, we are liable to code up an algorithm so that we can feed data into that algorithm and get data out, get answers or output. One way to think about machine learning is that it turns that around a little bit. We build a machine learning model and we feed it the data like you saw in the previous slides, the input and the outcomes that go with them. In other words, the input and the output. And we challenge the machine learning model to come up with the rules or the algorithm that allows it to find the patterns in the data so that it can predict answers or outcomes from future input. Before we start looking at some models and some actual code, I do want to define a couple of terms that are really important. One of those terms is supervised versus unsupervised learning. The two prominent types of machine learning models that we build today are supervised learning models and unsupervised learning. Supervised learning means we take a data set with labeled outcomes with one or more columns of data designated an outcome, like those examples we looked at earlier, and we train the model to do predictions for us so that we can feed in an input and have it tell us what the outcome will be. So another way to say that is that supervised learning trains models using labeled data. Those labels specify the outcomes. And the purpose of building and training a supervised learning model is to do predictions. In other words, to do predictive analytics. Unsupervised learning is a little bit different. It's typically not used to do predictive analytics. It's more often used to extract information from existing data. It typically relies on unlabeled data. A great example is maybe you work in the marketing department for a company and they're about to launch a new product and they want to try to target their marketing campaign to those customers that are most likely to buy the product. So what they might do is build an unsupervised learning model that uses all of their existing customer data to group those customers, to identify attributes that customers have in common and what might make them more likely to be interested in this new product. We're actually not going to do much with unsupervised learning in this presentation. Most machine learning models that are built today are supervised learning models. That's where we'll be focusing. And remember that the purpose of a supervised learning model is to do predictive analytics. One other pair of terms that I want to get out there before we dive into the code is regression and classification. There are two primary types of supervised learning models that we build: regression models and classification models. And the difference between them is very simple. The purpose of a regression model is to predict a numeric output. Maybe you feed in information like a person's age, their gender, their height, their weight, what part of the country they live in, and the output may be the probability that that person has heart disease or something like that. Regression doesn't necessarily mean we're using a regression algorithm in the machine learning model. It simply means that we are looking for a numeric output. Another great example, look at a face and predict what the age of the person in that photo is, something that it's relatively easy to do with ML and AI today. The other type of model is the classification model, and to be honest, these tend to be a little bit more common. The idea in a classification model is not to predict a numeric output, but to predict a class. So you have binary classification models and multi-class classification models. Let's say you build a machine learning model whose job is to look at an email and tell you reliably whether it's spam or not. That is a binary classification model because you're asking it to predict as output one of two classes, spam or not spam. On the other hand, if you're using machine learning to build a model that does optical character recognition, that looks at handwritten digits and determines what digit they represent, that is a multi-class classification model because there are more than two possible outcomes, all the different digits, all the different letters, etc. And the purpose of the machine learning model is to look at a bit pattern that you feed into it and for it to tell you which of those possible outcomes, the digit 0, the digit 1, the letter A, the letter B, and so on, it belongs to. So we'll be dealing with both regression and classification models. We'll also be talking about some of the subtleties of these and how you gauge the accuracy of them as well. So in all of the models that we build, this is the general process that we're going to use. And this is generically applicable to virtually any machine learning problem. It always begins with the data. Machine learning is not hard, by the way, if you have the data. Oftentimes, getting the data is the hard part. One of the reasons it's fairly easy to build, say, a spam detection model today is that there are numerous public data sets containing anywhere from thousands to millions of actual emails that humans have laboriously gone through and labeled each one as a 0 or a 1, as a not spam or a spam. If you have that data set, it's easy to build a model. If you don't have the data set, you may spend 99% of your time on the project just coming up with the data. Once you have the data, it almost invariably needs some cleaning and preparation. There are some common things that data scientists do here. For example, they'll look for duplicate rows in the data set, which could bias the model. They'll look to see how well balanced the data set is, and I'll say more about that later and even show you what that means graphically. If there are rows or columns with missing values, they'll decide, okay, what do I do with the missing values? Do I fill them in with imputed values? Do I remove those rows or columns? The right answer is very highly dependent on the problem you're trying to solve. But once you have the data and it's all cleaned and ready, now comes the fun part. Then we train our machine learning model with the data. We score it, which means we assess how accurate it is after training. And then we go back and we typically do some tuning. We can do some macro tuning by replacing the learning algorithm that we chose for the model. Maybe we started with naive Bayes as a learning algorithm, didn't work very well, so we're going to try logistic regression. And don't worry if those terms are new, I'll be explaining both of those a little bit later. Or if the model is reasonably accurate and we think we have the right learning algorithm, we then might tune that learning algorithm. That typically is done using a process called hyperparameter tuning. And rather than describe what that is, I'm going to show you what hyperparameter tuning is in just a bit, and also show you how we do it. If you go to grad school and study data science, or even undergrad school, my daughter, who just graduated with a degree in computer science, had a machine learning course in the fall semester of last year. And guess what? Because they wanted to teach them all the theory, they didn't let them use libraries. Everything had to be coded by hand. And guess what? My daughter didn't like machine learning a lot because it was really hard. In practice, we don't code up the hard stuff. All of these different learning algorithms that embody machine learning, like linear regression or polynomial regression, or naive Bayes or support vector machines, are already coded up in libraries like this one. Scikit-Learn is in all likelihood the world's most popular library for building machine learning models. It's a Python library, which is a big reason why most people, when they learn machine learning, they do it either with R or Python. And in my experience, it's more often Python. Even if you're a C# developer, you might learn Python to learn machine learning. So later you can take those skills and apply them to C#, especially now that with Microsoft's ML.NET, we finally have a world-class machine learning library for .NET developers. I'll be doing a webinar on that in a couple of weeks, by the way. But for today, we're going to do everything the way data scientists do it. We're going to build our models in Python, and we're going to rely heavily on Scikit-Learn. So that instead of writing 500 lines of code to implement linear regression, we can do it with 2 or 3 lines of code. And in fact, the first learning algorithm we're going to look at is simple linear regression. Now, when I use the term learning algorithm, that is the algorithm that we use in our machine learning model to allow it to find patterns in the data. There are dozens of popular machine learning algorithms. Which one is the right one depends on what you're trying to do. It depends on the shape of the data, etc. But almost all machine learning courses start with simple linear regression because it's very easy to understand. Take a look at the chart on this slide. If you think back to high school geometry, you may remember that the equation of a line is y equals mx plus b, where b is the y-intercept of the line and m is the slope. Given this equation, if I know m and b, I can plug in an x and I can compute y. So we have a data set here consisting of the blue dots you see. When I plot it, I can see that it is a fairly linear data set, and that's a clue to a data scientist that linear regression might be a good way to do predictions from this data set. And all linear regression is really doing is fitting a line to the data set. In other words, coming up with values for m and b in this equation so that in the future we can plug an x into the model and get a relatively accurate y. Now, I won't go into the math of how it does that, but I will say that most models that do linear regression use something called ordinary least squares. You basically start with a random line. You compute the error, that is the distance between that line and every data point in the data set. You square those errors, you add them up and take the square root, and then you adjust m and b to try to reduce that error. You do that iteratively, and typically after 10 or 20 iterations, if you've coded it up right, you come up with a line that is the best fit for the data. The good news is because we have libraries like Scikit-Learn to help us, we don't have to code that kind of stuff by hand. So let's look at our first example. And to do that, I'm going to pop over to Chrome here. And I'm going to use a tool that is incredibly popular with data scientists who do machine learning. The tool is called a Jupyter Notebook. Jupyter Notebooks allow you to enter and execute Python code. Some of them allow you to use, in fact, most of them allow you to use other languages as well, but Python is by far and away the most important one. Now, I could install a Jupyter Notebook server here, but instead, what I've done is gone into Azure Notebooks, notebooks.azure.com, where I maintain a number of different libraries and code samples that I share with others. And this is a free way to use my browser to do Jupyter Notebooks without having to install anything on my PC. And this is the first notebook. A notebook consists of cells. Cells can contain executable code. They can contain markdown for documentation or other things. But here you see a little bit of code. Now, if you're not familiar with Pandas, Pandas is an incredibly popular Python library for data analysis. I'm importing Pandas. The package has already been installed here in Azure Notebooks. And I'm importing a CSV file containing my data set. That CSV file is in my data folder, and its name is poverty.csv. In fact, if we go look in my data folder over here, we should be able to see the raw CSV file. Right here, poverty.csv. This is an actual data set that I pulled off of a public source online. It shows for each of the 50 states in the United States some statistics on poverty, including the percentage of people in that state that live below the poverty line and what the teen birth rate is per 1,000 people for people in that state. So one thing I might do is say, well, is there a correlation between the percentage of people in a state that live under the poverty line and the teen birth rate? If there is, and if the correlation is relatively linear, then I could easily build a machine learning model around this using linear regression. So I first bring in the data set. This function call right here on pandas reads the contents of the CSV file and returns a pandas data frame, which in a simple way of thinking is it's an in-memory table containing labeled rows and columns. The cool thing about pandas is once I have data read into a data frame, the data frame provides all sorts of functions I can use to do data cleaning and data manipulation and things like that. Here, the data is already fairly clean. I call head on the data frame just to get a look at the structure of the data. Head by default shows me the first 5 rows, but you can clearly see here the columns in there and what the values of those columns are for the first 5 rows. Now, I'm going to use matplotlib, another popular Python library, to plot those coordinate pairs. This is a 2-dimensional data set because all I'm really concerned about here are the percentage of people living below the poverty line and the teen birth rate for the state. When I plot it and generate this chart right here, I can see that, yeah, a linear model might be reasonable here because there is a relatively linear relationship between poverty rates on the horizontal axis and teen birth rates on the vertical axis. So let's build a machine learning model that will take a poverty rate and predict for me what the teen birth rate in that state would be. Thanks to Scikit, this is really easy to do. I start by creating an instance of Scikit's linear regression class. This is one of dozens of classes in Scikit-Learn that implement common learning algorithms used in machine learning. A machine learning model built around linear regression will attempt to fit a line to the data points and then use that to do predictions. So it takes one line of code to create the model and a second line of code to train the model. In Scikit, when I call a model's fit function, that's where the training takes place. Now, I'm not training with just an XY coordinate pair. If you go up here, X is actually all of the values in the poverty percentage column of the data frame that I loaded up here, while the Y's are the teen birth rates, all of the values in that column of the data set. So because there are 50 rows in the data set, I'm actually training the model with 50 rows of data here. Once that's done, and because the data set's small, it only takes a second or two to do the training, I then plot the data set again and use matplotlib to show the line that Scikit came up with to fit to the data. And visually, it looks like that's a decent model. How decent is it? Once I've trained a model in Scikit, if I want to use it to make a prediction, I simply call the model's predict method. So you call the fit method to train a model, and you call the predict method to make a prediction. You give it the input, and it tells me here that if the poverty or percentage of residents below the poverty line is 15%, it would expect the teen birth rate to be about 46. And in fact, here, if we start at 15 on the x-axis and go up, you can see that that is just about 46 right there. So it's a very simple example, but it shows how easy it is to do with Scikit-Learn. Obviously, the model's not going to be as accurate if we're dealing with non-linear data. And by the way, there's nothing new about this. Linear regression has been around for more than a century. Statisticians have been using it forever. Machine learning is just formalizes that and basically lets the model come up with the line as opposing to requiring the statistician to come up with it. And again, it's just one of dozens of learning algorithms, one of the simplest. Others are much more complex and capable of fitting to more complex data sets. So with that, let me pop back over here to PowerPoint. And let's pick up where we left off. That's a good start, but there's much more to know. So let me ask you a question. In that model that we just built and trained, how accurate is that model? In other words, if I plug in an X and ask it to give me a Y, would I expect that Y is dead on accurate? Is it within 10% or whatever? Well, the answer is we don't know, because it's never enough just to train a machine learning model and make predictions with it as I did there. You always want to score the model because scoring tells you how accurate the model is. And if you find from scoring that the model is not very accurate, that's probably when you would go back and try a different learning algorithm, something other than linear regression, for example, that might better fit the data. So how do you score a model? Well, it's really easy. In Scikit, when you are dealing with a regression model, you can simply call the model score function the same way you call fit and predict. The value that score returns is one between 0 and 1. It's called the R-squared value, also known as the coefficient of determination. The closer the value is to 1, the more accurate your model is at making predictions. The closer it is to 0, the worse the model is. What it really gives you is a numeric measure of the amount of variance in Y that can be explained by X values. So obviously you want R squared to be as high as possible. Now, for a lot of models, if you get the 90%, that's as good as you're ever going to get. Some models, you can't even get that good. Some machine learning models can be 99.9% accurate or more. It just depends on the data. And one mistake I see people make when they're first starting into machine learning is trying to get more meaning from the data than is actually there. One of the challenges in machine learning is to build the best model you can and to determine if you've achieved all the accuracy that's possible without trying to tie yourself into a pretzel and get information out that's not there. So I'm going to show you how scoring works in my next example. But before we do that, I also need to introduce the concept of splitting data. Scoring is essential because without scoring a model, you don't know how accurate it is. When you score, it is incredibly important that you do the scoring with a different data set than the one you use to train the model. Because if you score a model with the same data set you used to train it with, it's probably going to score pretty high. It may have learned that data really well, but that tells you nothing about how well the model will generalize, how it will respond when you present it with data it hasn't seen before. That's why we always want to score it with a different data set than the one we trained it with. The problem is we don't always have the luxury of having two separate data sets. In the real world, we often only have one. So what we'll do there is we will split the data set. We will take part of the data set and use it for training and a different part of the data set and use it for testing or scoring or validation. All of those terms are synonymous. Scikit even has a handy little function named train test split that will do that for us. We call it, as you see me doing here in this slide, specify the test size. In this case, 0.2 means I want a random 20% of the data set extracted into a separate data set that I'll reserve for testing. The remaining 80% will be extracted into another data set that I'll use for training. In this way, even if we have just one data set going in, we can split it up, doing an 80-20 split, a 50-50 split, or whatever you're most comfortable with, so to make sure that we score it with different data than we train it with. Something else I want to mention that's really important in machine learning is the concept of cross-validation. When you use train test split to split a data set for training and testing, which is incredibly common when we're using Scikit or even when we're using other libraries, realize that which 20% or whatever fraction of the data set you split off for testing was split off will affect the outcome. It will affect how the model scores. In fact, you can take one random 20%, test the model, and you'll get one R2 score or R squared score. Take a different 20%, run it through the same already trained model, you'll probably get a slightly different R squared score. Could be different by 10 or 15% or more. That's because unless you're dealing with a very, very large data set, there's just too much dependency on which part of the data set you subset for testing. So one solution to that is something called cross-validation, also known as k-fold cross-validation. The idea is this: rather than just doing one split on the data set, doing the training, then doing the testing, and then scoring it and assuming that value is correct, we will divide the data set into folds. 5 folds is very common, so is 10 folds in larger data sets. And we'll actually train the model and score it 5 times, each time using a different set of folds for training and testing. And then at the end, we will use the mean or the average of those scores to come up with a more accurate, more accurate measure of the model's accuracy, more reliable. That's the word I was looking for. So the downside of cross-validation is it takes time. If you do 5-fold cross-validation, the model is getting fully trained and scored 5 times. not a big deal for a small data set, but remember, there are machine learning models out there that take hours, days, even weeks to train because they're very complex and the data sets are so massive. There, if you are going to train the model 5 times, it's probably not reasonable to do that. But for smaller models, yeah, and it does give you a better depiction of the model's accuracy. Now, I want to show you an example that does this, but before I do, I need to introduce one other concept because it's something you're going to see in this model. This too is an important concept in machine learning. It's called categorical data. Machine learning models deal with numbers. They look at tables of zeros and ones, or zeros, ones, twos, threes, fours, etc., or tables of floating point numbers, and they find patterns that allow them to do predictions. But a lot of data sets have data that is not numeric. Data like the name of a color, red, green, or blue, or the breed of a dog. That data is string data. Machine learning models cannot deal with strings. So if we're going to use that type of data, categorical data in machine learning, we must somehow encode it or vectorize it, turn it into numbers so that it can be used in a machine learning model. And there are 2 common ways that's done. One is called label encoding. The other is called one-hot encoding, and the latter of those 2 is by far the more common. In fact, it's used a lot in machine learning models. We're going to use it in this next example, and this is what one-hot encoding is. Let's say you have a data set like the one in the lower left of this slide, where there's a column named company with string company names like Microsoft and Google and Facebook and others. Well, again, a machine learning model cannot process that string data. But if you one-hot encode the data, it can. And one-hot encoding does to the data set what you see on the right. For each unique value in that company column, or the categorical column as we'll call it, for each unique value in that column, an additional column will be added to the data set where the name of the column is the value of that entry, and a 1 or a 0 appears in the cells underneath, depending on what the value was in the original data set. You can see that here. Now, one downside, you can imagine if there are thousands of different unique values in that column, yes, it's going to add thousands of columns to your data set. But for the most part, while you always like to deal with fewer columns rather than more if you can, for the most part, machine learning is very good at dealing with lots of data, including lots of columns. So that is what one-hot encoding is. It is the most common way to turn categorical data into numeric data that a model can understand. Scikit has a function, actually a class named one-hot encoder that will do it for you. Or if you're using pandas, and you almost always are when you're using Python and Scikit, you can call get dummies on a data frame to do the one-hot encoding as well. So let's look at an example. We're going to do one more look at regression here, but this time it's going to be a little bit more complex and a little bit more real world. This one demonstrates multiple linear regression. Now, in the previous example, we built a simple linear regression model. Simple linear regression means we're dealing with 2-dimensional data, X's and Y's. In the real world, data sets are typically a lot more complex than that. They have multiple dimensions. We can still use regression to build a model for a regression model for a multi-dimensional data set. And when we do, we call it multi-dimensional or multiple linear regression. So this time I'm using a different data set. It's a CSV file named PacificHeights.csv. I'm loading it from my notebook project here. Then I'm calling head so you can get a look at what's in the data set. It has columns with names like address, bathrooms, bedrooms, finished square footage, etc. This is actually real data that came from real estate sales in San Francisco, where I lived many, many years ago. And one of the things it does is it includes last sold price, how much that dwelling last sold for. So what I want to do is try to build a machine learning model that can take data like the number of bathrooms in the dwelling, the number of bedrooms, the finished square footage, and have it tell me what the expected selling price for that house would be. So as usual, I call read CSV in pandas to read the CSV file, create a data frame. I then call a data frame function named core, which is really interesting. One of the things that you always want to know when you're dealing with multidimensional data is which of the columns affect the outcome, the predictions that I'm trying to make the most. And the data frame's core function will give you that. If I want to know to what extent the other columns in the data set affect the last sold price column, then it looks like finished square footage. It looks like there's a strong correlation between finished square footage and last sold price. There's not much of a correlation between the latitude of the dwelling and the last sold price. So one reason that I do this is if there are values in here that really don't affect the outcome much, I may just eliminate those columns altogether when I train my model. But before I make that sort of decision, I also have something else to do. Notice that there are categorical columns in this data set. There's a column named neighborhood with the string values like Pacific Heights, column named use code with string values like condominium or single family, things like that. Even the address column is a column of categorical values. I'm not going to use the address column or even the zip code column because zip code, there's not a terribly strong correlation between zip code and the last sold price. But notice that there is actually, that's zip code is not categorical, it's a number. Notice that there is no entry in here for the use code column because that's a categorical column. And unless I convert it into non-categorical data, Core doesn't know how to deal with it. So what do? I use the data frame's getDummies function to one-hot encode all of the values in the dataset's use code column. Then if I look at the resulting dataset, or in pandas the data frame, you'll notice that additional columns have been added, one per unique value in the use code column. Now the data has been one-hot encoded, and if I call Core on it again, I can see, wow, looks like whether the dwelling is a duplex has almost no bearing on the last sold price. But whether it's a condominium or a single family dwelling, looks like that has a lot of effect on the outcome. So what I'm going to do now is build a filtered data set using a subset of the columns that have the most bearing on the outcome, including those one-hot encoded columns there. And then I'm going to check the correlations again. And you can see there's a pretty strong correlation between every column in this data set and the last sold price of the dwelling. Do a little bit of charting. I'm just curious, is this data set relatively linear? Well, I could separately plot all the variables or columns against one another. And sometimes data scientists do that, but I picked one of them and it looks like, yeah, there's a relatively linear correlation between finished square footage, for example, and last sold price. So guess what? I'm going to use that same, excuse me, linear regression class in Scikit to build a multiple linear regression model. One line of code does it. One line of code, a call to fit, does the training. By the way, notice the call to train test split because I've got only one data set. I did an 80-20 split so that I can use 80% of the rows in the data set for training and 20% for testing. And that's what I passed to the model for training. Now, how accurate is the model? Well, I can call score on it and I get 0.55. That's the R-squared score, or the coefficient of determination. That's not a great score. It says that only about half of the variance in the last sold price can be explained by my input variables, but it's a good start. I also don't fully trust this because I did this scoring using one random 20% of the data set, basically 20 rows pulled from random places. I'll get a more accurate estimation of how good this model is by doing cross-validation. So what I do is call Scikit's cross-val score function. I pass in the model, I pass in the X's and the Y's that I want it to do the scoring with. And with the CV equals 5 parameter, I'm saying use 5 folds. Train this model 5 times with 5 different folds from the data set each time. And it tells me, okay, I did that and I get these accuracy scores. Notice they range from 0.61 up to 0.76. I take the mean of those, or the average. 68% is a better estimation of how accurate this model is. So you can see when I just called score using a randomly selected 20% of the data set for scoring, the 55% I got back was not really very good. Now, this may or may not be acceptable here. The truth is, in this data set, you can do a little bit better than this, but not a whole lot better. But there is not a perfect correlation between any of the variables in this data set and the outcomes. So that's a quick look at multiple linear regression. Let's go back to the slides here, right here, and see what else we can learn about. I want to mention quickly that there are lots of other learning algorithms, not just linear regression. You can do polynomial regression really easily in Scikit, for example, where you fit an nth order polynomial to the data, which is useful when the data follows some rather predictable curve or set of curves as opposed to being linear, but those aren't used very much. One learning algorithm that is common is something called the decision tree, where we're not fitting data to an equation at all. We're not trying to come up with coefficients in an equation. Instead, we build a binary tree in memory from the data, like this one. And then when we run the model, when we ask it to do a prediction, it tends to be super, super fast because all the model is doing is taking the values you input and walking down the branches of the tree that it built during training to arrive at an outcome. Now, Scikit makes this easy. It has a couple of classes that implement decision trees. One of them is for regression models that produce numeric outputs. The other is for classification models that do classification. But the truth is, decision trees are not often used alone. Why? Because if you don't constrain those trees, if you allow them to grow deep enough and wide enough, they can basically memorize a training data set, which means it'll score really well, or at least it will appear to train really well, but you really have no idea how well it's going to respond to data it hasn't seen before. So in real life, while decision trees themselves are rarely ever used, random forests are used a lot. These are incredibly common in machine learning. Random forests are collections of decision trees, but each tree in a random forest is different. Typically, the subtrees, if you will, are created from randomly selected subsets of the data set or even randomly selected columns in the data set. You may build 50 or 100 or 500 or 1,000 decision trees in a random forest, and then when the model is run, all of those decision trees are used and their results are averaged to give you a better model. The nice thing about random forests is that they are much less prone to overfitting. Overfitting is a term that means, well, the model is so good it learned the training data well, but it's not going to generalize well. It won't respond well to data it hasn't seen. By purposely not allowing any one tree in a random forest to learn all of the data and learn it well, by running all the trees and getting an average, we typically get a model that is not prone to overfitting. I'm going to show you a quick example that uses this, but also want to introduce the concept of hyperparameter tuning. Once you've arrived at the right learning algorithm, whether it's linear regression or something else, random forest, typically those algorithms accept a number of parameters. And the next task is to refine the model by finding the right combination of parameters, the combination that produces the most accurate model. And here again, Scikit makes this easy. It has 3 classes that make it easy. Let me just show you a quick example here back in my Azure notebooks. This one is called Random Forest Regression. I basically take that same Pacific Heights data set you saw earlier, but I fit a random forest to it to see if I can get it more accurate. So most everything I'm doing at the beginning in terms of doing the one-hot encoding, determining which columns most affect the outcome and stuff, I'm still doing. In fact, I'm doing exactly the same way as I did before. The difference is, instead of using linear regression, I use Scikit's random forest regressor class. And right out of the box, I get what appears to be a more accurate model. If I do a cross-validation, I find that it's marginally more accurate than the linear regression model, but not much. But guess what? When I created an instance of Scikit's random forest regressor class here, I accepted all the default parameters to that learning algorithm. Now I'm going to do some work to see if there's a better combination of parameters. So I can use Scikit's grid search CV function to do that. CV stands for cross-validation. What I do is I pick the various parameters that the algorithm takes. Random forest regressor takes about 15 different parameters. I specify what parameters I want to vary and what values I want to vary them between. And then I call fit on the grid search CV instance rather than model. Now this is going to take longer. In this case, this model is going to be trained, 2 times 3 is 6, times 2 is 12, or times 3 is 18, times 3 is 48, so this thing's going to train almost 150 times. It's going to take a lot longer to train. But at the end, I'm going to find out from the best estimator property in the grid search CV object which model gave me the best accuracy. And lo and behold, when I use that model and cross-validate it, I'm up to about 72% accuracy as opposed to the 68% I had back here. So grid search CV is one way, probably the most common way to do hyperparameter tuning in Scikit. And while it takes longer because the multiple is being trained many times, it is a very efficient way to find out once you've chosen a learning algorithm, what combination of parameters passed to it will give you the best result. Now, we've only got about 10 minutes left, so I'm going to have to hurry, but there is some stuff I want to show you. Everything that we've dealt with up to now has to do with regression. Let's talk about classification models because these turn out to be some of the most interesting ones. It is these models that will look at an email and with a high degree of accuracy tell you whether it's spam or not. We'll do OCR. In fact, one of the early machine learning models that was put into practice was done by the US Postal Service about 30 years ago when they needed a computer to scan handwritten zip codes on envelopes, translate that into actual zip codes so that they could automatically sort them. It was a classification model that they built to do that, and I'm going to show you in just a moment what that model looks like. So there are lots of different classification algorithms in machine learning. One of the most popular is one called Logistic Regression. It works with both binary classification problems, spam or not spam, or multi-class classification problems like identifying a face in an image from a set of multiple candidates for that face. Scikit provides helpful classes and functions to help you implement logistic regression, and I'm going to show you a model here in just a moment. Before I do that, I want to make you aware scoring a classification model is very different from scoring a regression model. With regression, we most often use that R-squared score, or the coefficient of determination, to gauge the accuracy of our model. There is no R-squared score for a classification model. Instead, there are several different metrics that we use, and which one or ones we use typically depends on what we really care about. For example, in a case where maybe using machine learning to look at x-rays and determine whether a bone has been broken, you would rather have false positives there than false negatives, because you'd rather tell someone that the bone is broken when it's not so they can get it checked out more than tell someone who has a broken bone that the bone's not really broken. Then they don't see the doctor and they're going to be hurting for a long time. In that case, you might choose precision as the metric that you want to use to score your classification model, because it gives you it factors false positives into the score. If you don't care so much about false positives, and in fact, if they're okay and you'd rather lean towards false negatives, if there's going to be error, you may care more about the recall. And those are only two of many metrics we use for classification models, but let me show you an example here. Here's what the post office essentially did 30 years ago to allow handwritten digits in zip codes to be machine read and sorted. Back to my notebooks here. This one is called, let me back up here, digit classification, and it uses logistic regression to look at bit patterns like this one, scanned handwritten digits, and there are multiple data sets available out there in the public domain for training machine learning models like this one, by the way. I'm using one of the public ones here that's so common, it's actually built into Scikit-Learn as a sample data set. It takes scanned handwritten digits like these. These are 8x8 scans, and it predicts what digits 0 through 9 it belongs to. So real quickly, this data set is built into Scikit. I'm loading it right here. This is what one of the digits looks like. It's an 8x8 array of values from 0 to 15. A higher number means there's more ink in that cell, if you will. So this 0 that you see right here is numerically represented with this NumPy array right here. In fact, here I'm plotting the first 50 scanned and handwritten digits in the data set just so you can see what they look like. And you can see that, one 3 is not like the other 3. There's quite a lot of variation here. So by the way, up here, also want to know how big is the data set. This tells me there are almost 1,800 different digits represented here, each in an 8x8 array. And here I'm looking at the balance. Here's something that's important. When you build a classification model, you always want, to the extent you can achieve it, a balanced data set. That is, you want there to be a roughly equal number of rows in the data set representing each of the possible outcomes or classes. Here, I'm plotting that in a histogram, and you can see that this is a pretty balanced data set. There are about the same number of scans representing zeros as there are 1s, 2s, 3s, and so on. Now, I do the train test split to carve off 20% of the data for testing. I use Scikit's Logistic Regression class to implement a logistic regression model, and I train the model by calling fit. Now, before I ask it to do a prediction or score it, here I'm using Scikit's confusion matrix function. This is one way to assess the accuracy of a classification model. Here there are 10 possible outcomes, each of the digits 0 through 9. And what this tells me is, for each digit in the test set that it looked at, what it guessed the digit to be and what the digit actually was. What you want to see here are big numbers along the diagonal right here, because that means, for example, here in 34 times when it was asked to look at the scan for a 2, it correctly said it was a 2. One time, however, it incorrectly predicted that 2 was something else. So by looking at the confusion matrix, to the extent you see big numbers along the diagonal and zeros or very small numbers elsewhere, you've got a pretty good model. When we score the model, it tells us that we've got 95% accuracy. But remember, that's just one way to assess the accuracy. We can also ask for measures like precision and recall, an F1 score, which is the harmonic mean of the precision and recall. All of those can be had with simple Scikit functions like these, and you can see that here, in all cases, it looks like this model is about 95% accurate at looking at a scanned handwritten digit and determining what digit it belonged to. So I realize it's 3 o'clock. I'm going to go on just a few more minutes, if that's okay. If you need to get off to a meeting, or if your lunchtime is over and you need to leave, feel free to do that. You're not going to hurt anyone, but I'm going to show you some really cool stuff in this next 10 minutes or so. And then I promise I'll shut up. We'll see if we can take time to take a couple of questions as well. So that is one look at classification. What about classifying text? How do we do sentiment analysis on text strings? How do we look at an email and determine whether or not it's spam? Well, once more, we somehow have to convert all of the text into numbers, into vectors, as we sometimes call them, because machine learning models find patterns in numbers. They don't know how to deal with text. So at a high level, to vectorize text, what we typically do is we first prepare the text. We'll convert all the text to lowercase. We'll remove common words like the, am, I, we, are, not, things like that, because they typically have little relevance to the outcomes we're looking for. We'll even remove punctuation symbols, get rid of multiple spaces and stuff, so that we have a very clean corpus of text to train with. But beyond that, we vectorize it. And I'll show you what vectorization does, but realize that in Scikit there are 3 classes to make vectorization, which can be relatively complex, very easy. Foremost among them, and the most commonly used, is a class named CountVectorizer. Here's how it works. Let's say that we want to train a machine learning model with 2 snippets of text, the quick brown fox and jumps over the lazy dog. Maybe we're going to do sentiment analysis. Maybe we're going to build a spam detection model. But whatever we're going to do, we must first vectorize that data set, turn the words into numbers. If you use Scikit's CountVectorizer class, it does this. If you look in the lower left corner of the slide, it builds a table in which there is 1 column for every unique word found in the text. Notice I've factored out words like the already, and has 1 row for each piece of text in the data set. In this case, there are 2 rows because there were 2 text strings. And look at the zeros and the ones. The quick brown fox equates to quick brown fox since we removed the stop word the. And in that first row, you see ones under quick, brown, and fox. So we build this typically very large table, mostly zeros, but with ones where corresponding words appears in the text. That is called text vectorization. It's called count vectorization, whatever you want to call it. Once I have that table of ones and zeros, then I can deal with that text. Let me finish up by showing you a couple of notebooks that use this, and then give you a URL for the GitHub repo where you can download all of these notebooks and more, ones that I didn't have time to show. So let's go back for just a moment to my notebooks, and I first want to pull up one called email classification. About 20 years ago, we made a great leap forward in building spam detectors by applying machine learning to the problem. It was a very difficult problem to solve without machine learning, not difficult with it. Here is a machine learning model that does pretty accurate spam detection. I start off with a data set in this CSV file. This is one of a number of public data sets that are available. The nice thing about it is someone has gone to the trouble of taking the 1,000 different emails in this data set and labeling each with a 1 or a 0, that is a spam or not spam. It's a relatively small data set. We could make it more accurate by training it with more data, but the nice thing is it's pretty accurate as is, and it trains rather quickly. So I load the data set. I call head on the resulting data frame, so I can see the data set has a column named is spam, where 0 means it's not, 1 means it is, and it has a column named text, which contains the text of the email. And in this case, a lot of the work of preparing the text, converting everything to lowercase and all, has already been done, so I don't have to do it here in Python. One of the things I do here is I want to know if they're duplicates. It turns out there is 1 duplicated row in the data set. So here I identify that row and I remove it by calling the data frame's drop duplicates function. Now I only have 999 emails to train with, but hey, I don't want duplicate data biasing my model. So what do I then do? I use Scikit's CountVectorizer class to vectorize the text. And I'm using just a few of many options it presents to me here, but some of the most important ones. Here I'm telling it, if these words appear in the text, get rid of them. Now I could provide a more extensive list of stop words. I could let Scikit's CountVectorizer class use a built-in list of stop words, or I can use an external list. But I just wanted to show you here that it will remove stop words for you. I can also set n-grams, and an n-gram is this. By default, every word the CountVectorizer vectorizes is considered to be independent of all the other words, which means if the words credit and card appear right next to each other, they'll be vectorized the same as if they appeared far apart. Now, you and I know that if the words credit and card appeared next to eeach other in an email, that might be an indicator that it's more likely to be spam. So with n-gram range, I'm saying I want you to consider not just individual words, but combinations of up to 2 words that appear together. This will increase the memory requirements for the model. It will increase the training time because now the data set that's being built internally not only contains 1 column for every word in the emails I train with, but one column for every pair of words, but it may give me a more accurate model in the end. As usual, I use Scikit's train test split function to do an 80-20 split. I use the multinomial NB class in Scikit. That stands for multinomial naive Bayes. Naive Bayes is a very common algorithm used to do text classification. And once the training is done, that is, once fit returns, I look at a confusion matrix, and it looks like it's a pretty decent model. 101 times when presented with an email that was not spam, it correctly identified it. Twice it said, no, it is spam. If I call score in the model, it says it's about 98.5% accuracy. Here I'm using yet another measure of the accuracy of a classification model. This one stands for receiver operating characteristics area under curve. Without going into details, it is in many cases, in this case in particular, which is a binary classification task, a more accurate indicator of how good this model is. Well, let's just see how good it is. So let's test it. Look at this. I want to find out if this email, can you attend a code review on Tuesday? Need to make sure the logic is rock solid. Is that valid or is it spam? Well, we vectorize the text, we feed it into the model by calling predict, and it tells us it's not spam. If we call predict proba in Scikit, it actually gives me the probabilities that Scikit predicted for each of the two possible classes. It tells me there's a 99.999% chance it believes that this message is not spam. It's just an infinitesimal chance that it is. What about this message? Why pay more for expensive meds when you can order them online and save dollars? Guess what? It tells me, yeah, that's spam. How sure is it? 99.999 something percent sure that's a spam message. So here, with a little bit of code and a relatively small public data set that was already labeled spam and not spam, we can really do a good job of looking at an incoming email and deciding whether it's spam or not. Just real quickly here, one other example you might want to look at that also involves text classification is sentiment analysis. So this is a pretty common task in machine learning these days. Maybe your marketing department wants you to build something that looks at tweets that target your company, that programmatically determines whether the tweets are positive or negative and how much so that it could raise an alert on a dashboard or email the head of marketing if things are trending negative, something the marketing department needs to get on top of. Pretty easy to do. I'm using a public data set right here. It comes from the International or Internet Movie Database. It has something like 50,000 reviews, I believe, that are each labeled as 0 for negative or 1 for positive. And I do all the stuff in this model you saw me do originally. I take the training data set, I vectorize it using Scikit's CountVectorizer. I tell it to use n-grams up to 2 words in length. Here are the stop words I want to get rid of. I call train test split to split off 20% of the data for testing. And this time I use the Logistic Regression learning algorithm. This is the same one we used to do OCR on those digits a couple of demos ago. And it looks like I get about 90% accuracy, even without any hyperparameter tuning. In fact, we can test this. So the long lines and poor customer service really turned me off. I think you and I would agree that's a somewhat negative review. Well, our model scores it as a 0.16. In other words, on a scale of 0 to 1, this is much closer to negative than it is positive. But what that number actually is the probability that this is a positive review, by the way. On the other hand, if I feed in one of the most delightful experiences I've ever had, very positive review, it scores that as a 0.838. So in other words, it's not incredibly positive, it's not a 1, but it is pretty darn positive. So there are 2 examples of how we use text vectorization in Scikit in order to build machine learning models around textual data sets. There are other examples as well, but hopefully that will give you something to start with. Now, I've got some more demos we can do, but that we won't have time to do. I will show you this real quickly. And I promise I'll end after this. One of the most interesting learning algorithms, one of the more advanced ones, is something called SVM, or support vector machine. These have come into prominence in recent years. And the bottom line is that if you have a model with sort of a difficult data set where linear regression doesn't work, naive Bayes doesn't work, et cetera, oftentimes support vector machines can find patterns in the data. And the way support vector machines work is this. Now, when you read the papers, you look at the math, you can get lost pretty quickly. But here's what's really going on. In the upper right corner of this slide is a data set. It's a two-class data set. You have those black dots that are sort of clustered around the origin and the blue squares that are further out. Because the points are arranged circularly, there's no line you can draw in that coordinate plane to separate the blue squares from the black dots, and yet SVM can separate them easily. How does it do it? It adds dimensions to the data. Suppose you were to take those blue squares and black dots, each of which has an X and Y coordinate, and you were to add to it a Z coordinate that's computed from the X's and the Y's. If you did that, and you then rotated the data set 90 degrees around the X-axis so that you're looking at it as in the diagram on the lower right, because the blue squares are further from the origin, their Z's will be higher. They'll be further away from that X-axis, and look at that. Now, in that third dimension, we can draw a line or plane that cleanly separates those things. So SVM, mathematically, it can be incredibly complicated, but in Scikit, we have a couple of classes that make it easy. There's linear SVR for regression using SVM, and linear SVC and SVC for classification models that use SVMs. And I won't go through this demo, but I'll make you aware of it because it's in the repo whose URL I will give you. It's a pretty cool one where we do facial recognition without using a neural network. In real life, they're typically done with neural networks, but we're doing facial recognition using a classic machine learning model. That model is built from a support vector machine. So again, I won't go through it here, but you can download this notebook and run it for yourself if you want. And basically, we take a bunch of facial images from a public data set called Labeled Faces in the Wild. We train an SVM model that is, at the end of the day, about 88.5% accurate at looking at a face that we provide to it and telling us what person that belongs to based on the facial images that we train the model with. Really fun thing to look at and to play with if you want to go a little bit deeper here. So I will close out by giving you a URL. This URL points to a public GitHub repo where you will find these notebooks and these data sets that I've shown you, as well as some that I haven't shown you. And feel free to check back in that repo from time to time, because I'm constantly adding new notebooks with new models, tweaking or refining existing models and stuff like that. And there are a lot of really good examples there showing everything from linear regression to logistic regression to naive Bayes to support vector machines. There are even some good example notebooks showing something that's often important in machine learning called PCA, or principal component analysis. So feel free to go there, pull the content down. If you want to use them in a class of your own or share them with your colleagues, feel free to do it. Again, that repo is public, and I put this out there just to make it easier to learn. So I apologize for going over, but I hope that it was worth your time. We'll be doing additional webinars. We have one coming up in a couple of weeks on machine learning for C# developers, where I'll do a lot of the same stuff, but instead of using Python and Scikit, I'll be using C# and ML.NET. And later on, we will do one on deep learning as well. I love neural networks, and there are a lot of stuff that I'd love to show. Now, for those of you that do have a little bit of additional time, let me check and see if there are any questions, because I'd be happy to answer a few of those as well. Let's see here. Let's see if I can.
There are, Jeff. Can you see them?
it's showing me one question at a time because the window's so small. Let me try and maximize. No, that's just moves the window. So I can see half of one line at a time, Rachel. Let me see. Okay, it does let me make that a little bit bigger. Wow. So yeah, let me show you what I'm seeing, Rachel. How do I make it so that I can see more than this right here? That is crazy.
Jeff, do you want me to read them to you so you can at least hear them?
Yeah, or better yet, since we don't have time for too many, I'd love to be able to see it. But there doesn't appear to be a way to resize that. Yeah, Martha, why don't you pick a few and read them off?
Okay, and there's about a half dozen of them. And Fabian
Good, we
said,
take them all then.
What's that?
We can take them all then.
Okay, awesome. Okay, so Fabian said, I'm very excited about ML, and I think it's AI, and I thought it would be good to use the technologies for improving some real life. Sorry, I had to scroll down too. Some real life desktop apps for manufacturing production. My enthusiasm disappeared once someone told me that unless I have data sets with millions, hundreds of millions of data points, the whole idea is useless. Typically, I deal with data sets a few thousand at a time. Is there any hope?
There is hope. It depends entirely on the nature of the data, the nature of the model you're trying to build, Fabian. But you saw one example here where I built a pretty darn accurate spam classification model using just 1,000 emails. Could I make it more accurate with more emails? Yes. So whether you really need millions of rows depends a lot on how much variance there is in the data. One nice thing about scanned handwritten digits is that while 10 threes may all look somewhat alike but a little bit different, they're going to look very different for most of the sixes, for example. So what we find in a data set of scanned handwritten digits is a lot of uniqueness, if you will, between the samples. And when that's the case, you can often build a very accurate model with relatively low volumes of data. When the data set is designed to do something where there's less uniqueness, like you're training a model to do facial recognition, in that case, you typically do need a lot of data to make the model accurate. So the short answer to your question, is there hope? There is hope. Really depends on what you're trying to do with it. So what else do we have, Martha?
Eduardo wants to know, is there a way to run git search CV, I don't know what that funny mark is, Eduardo, sorry, over and over again with different parameters to see which combination yields the best ML model?
Yeah, oh yeah. So grid search CV, I mean, you can run it once with lots of parameters, multiple times with different parameters. You could even run it once, get the optimum model based on those parameters that you specified, and then you can ask it not only for the best model, but what the parameters that were best are, and then you could do another pass with grid search CV with values that center around those parameters you used the first time. I'll bet that's what Eduardo was thinking about. The answer is yes, we do it all the time because when you use grid search CV, you're using discrete values for each parameter. When it finds the best ones, the next question to ask is, well, what if I had entered more discrete values around the one it found to be best? So yes, and we do that all the time.
Okay, Shirka is asking, what is the impact to model metrics if duplications are not removed from the training data?
Yeah, it's a good question, and I hate to say this, but it does depend somewhat on the model and on the learning algorithm. But generally speaking, if there is a substantial amount of limited data, of duplicated data, it could bias the model. Probably bias it towards the duplicated data, could duplicate it away. But you know, if you have 100,000 rows in your data set you're training with, and there are 5 or 10 duplicated rows, you're not going to see a difference. If you have a data set of 1,000 rows, and 25 rows are duplicates, you're not going to produce the most accurate model you could get because of that duplication. In fact, the model could believe that it's more accurate than it really is and mislead you. So depends on the proportion of the number of duplicated rows to the total number of rows in the data set, but it is never a bad idea to get rid of those duplicated rows.
Okay, we've got a few requests for some books for ML novice to shore up the math and the algorithms, as well as the C# machine learning library. Oh, what was the machine learning library you were referring to earlier also?
Yeah, so the C# library I'm referring to is called ml.net. It's a relatively new open source library from Microsoft. It's the one we'll be doing the webinar on in a couple of weeks, and it's amazing. I love it, Martha, because C# is my favorite language by far. I learned Python just for machine learning, but given a choice, I'm always going to do it in C#. The problem was until recently, the best libraries for machine learning were only available in Python. Well, I shouldn't say only available. They were primarily Python libraries. So now with ml.net, I can do all of this in C#. But in terms of just learning the basics, there are a couple of books I could recommend. I'm actually pulling them off my shelf right now. One of them is, it's an O'Reilly book. It's called Introduction to Machine Learning with Python. It has lots of good examples. Yes, they are in Python, but it also does a really good job of introducing concepts like scoring, underfitting, overfitting, hyperparameter tuning, explanations of the different learning algorithms, and most of those explanations are independent of the language that you're working in. So again, the title of that book is from O'Reilly is Introduction to Machine Learning with Python. There's another one I like quite a bit. I refer to it myself sometimes, and it is called it's also an O'Reilly book. It's called Hands-on Machine Learning with Scikit-Learn and TensorFlow. So it not only covers statistical machine learning like we looked at today, it also goes some into deep learning, building neural networks with TensorFlow, which is the most popular library used for building those models. There are others as well, but those are two of my go-to books.
Okay, Monty wants to know, does ml.net have any of the same capabilities as Scikit, S-C-I-K-I-T?
Yeah, in fact, ml.net in some ways was patterned after Scikit. 90% of what you can do with Scikit, you can do with ml.net as well. And guess what? There are things you can do with ml.net that you can't do or can't easily do with Scikit. So I'll say a lot more about this in the webinar we do in a couple of weeks, but let me throw this out there for now. The really cool thing about ml.net, besides the fact that I can program it natively in C#, is that it's not something where some smart people at Microsoft sat around a table and said, you know, we need a good machine learning library. Microsoft has been using AI and ML in their products for years. And for years at Microsoft, they had an internal library available only to employees that implemented all the machine learning algorithms and stuff like that. ML.net came from that library. It took them more than 2 years to do it, but a small group of programmers at Microsoft got permission to clean the library up and open source it, and that is the library we call ML.net. What's great about that is, you know, sometimes we say you don't trust a Microsoft product until it's in version 3, right? Well, I think ML.net is up to version 1.5 now, and it's already very robust because the algorithms embodied in it have been used within Microsoft for literally years, some of them more than a decade.
All right, a couple more. So Rafael and Christian were both asking about the book, so thank you for that. Marius was doing the same. Okay, so Jesus wants to know, based on your experience, is online training just as valuable as formal college degrees as companies look for talent?
That's a great question. It depends on somewhat on what your goal is. I tell you this, and I'll use my son as an example. My son got an undergraduate degree in economics a few years ago. But then he got the data science bug, and he did some learning on his own, but he ultimately decided that to get a job with one of the companies he wanted to work for, he needed a degree. So he went back to grad school and he got a master's degree in it. So, and the company he works for, I feel pretty sure would not have hired him to do what he does without that master's degree. However, that doesn't mean you have to have a master's degree. I've met a lot of really smart people who know a lot about ML and AI, who have degrees in, engineering or music or philosophy or whatever. They're primarily self-taught. I can tell you that at Wintellect, when we hire folks like this, we typically don't care what kind of degree you have or if you have a degree. What we care about is how good you are at what you do. We look for the best, and if you're good at it, we don't care what your credentials were. So it depends a lot on, what your goal is with it. There are a lot of really good resources for learning this stuff, and in some ways you can learn more about it with those resources than you do in university. It's funny, when my daughter went through that machine learning class in college last fall, it was a senior level class, and I was really curious. I wanted to see how it was taught. Will the professor, bury them in equations and make them code everything themselves? The answer is yes. So what would happen is my daughter and her friends would sit through a lecture on support vector machines. Then they would call me that night and say, "Dad, this just makes no sense at all. What are they?" And I would show them a diagram like the one I showed you, and they would say, "Oh, why did my professor say it that way?" So not to discount that degree at all. It's going to be necessary for some jobs. But I tell you what, there are a lot of great learning resources out there that might teach you more than what you would learn in a graduate school course. And at the end of the day, the people that are best at this are those that roll up their sleeves and learn it and do it, because you learn by doing. There's really no shortcut to that as far as I know. I realize that was a long answer to a short question, but hopefully that helps.
All right, Nicholas wants to know, can you use Python Jupyter in Visual Studio Code?
You can. In fact, I was using Azure Notebooks to host my Jupyter notebooks here, but there's a free Jupyter plugin for Visual Studio Code. So you can load those IPYNB files that contain a Jupyter notebook into Visual Studio Code and run them right there locally on your machine. And in fact, there's some advantages to doing it that way, because if you've got a machine with a lot of horsepower, a lot of RAM, maybe 4 cores in the CPU, even an NVIDIA GPU, you can probably train these models faster on your local machine through Visual Studio Code than you can in an Azure Notebook, where you're being granted free but limited resources in Azure to do that training. So yes, look for the Jupyter plugin for Visual Studio Code. It's free. Then you can open those notebooks right there in Visual Studio Code and run them locally.
Okay, Eduardo was asking about graduate programs. He's a lot of courses. A lot of the courses are more for software engineering courses. Are there any machine learning or AI grad schools online programs that you would recommend, or anyone that you recommend I talk to?
Well, I can't speak to the individual programs. On behalf of Microsoft, we have in recent years visited most of the universities in the U.S. and a few in Europe that have big names in data science. So I've been to Stanford, MIT, Berkeley, Cornell, University of Illinois, Champaign-Urbana, lots of others, and interact with the students and faculty there. They're all big name programs, and they're all very good. I don't know how many of them offer online curricula. I will say that one of the most highly regarded online curricula for machine learning comes from Stanford University. It's marketed, I believe, through Coursera, so you need to be a Coursera member, but they have a seminal online machine learning class that goes through a lot of the theory. Sometimes it gets a little heavy on math and stuff, but it's a very good course.
Okay, Marius is dating you. Thanks for getting me started on programming. My first programming book ever was Programming Windows with MFC many years ago when I was still a little boy. Ha! Take that, Jeff.
Yeah.
That was good.
Well, you've probably heard me say this, Martha. When someone says, "Hey, Jeff, I remember your books from way back when," the first thing that comes to my mind is, how old are you? So
That hurts.
thank you very much. It is always a blessing to have someone say, hey, Jeff, I learned how to program from one of your books years ago. I never get tired of hearing that. So thank you.
All right, IM wants to know, do you think using a deep learning model based on Keras, for example, would perform orders of magnitude better than ordinary machine learning algorithms? How about features engineering and their incidence on the model accuracy?
Yeah, there's a lot to unpack there, and it tells me we do need to schedule a webinar on deep learning as well. I've got some really good examples. So with regard to deep learning via neural networks, will the model be orders of magnitude better? And I assume by better you mean more accurate? No. I could take any of these models that I showed you today. I could recast them as neural networks, and most of them would be a little bit more accurate. Some of them may be quite a bit more accurate, but orders of magnitude, no. One of the nice things about deep learning is that feature engineering is a little bit less important. With statistical machine learning like we did today, it is really important to understand the structure of the data, to do things like understand which columns, for example, might be collinear. If you've heard of that term before, one of the things you want to avoid is having two columns that are basically related to each other, both affecting the outcome. We call that collinearity, and it can not only bias a machine learning model, it can in extreme cases even prevent the model from converging on a solution. One of the nice things about deep learning is it cares a little less about the structure of the data. It's better able to work through those sorts of things. Deep learning models do tend to take longer to train, sometimes orders of magnitude longer. So let me just say that for the kinds of problems that you saw here today, sentiment analysis, optical character recognition, regression, all of those could be done with a neural network, but a neural network typically doesn't offer any substantial advantages. There are, however, many problems that can be solved with deep learning and neural networks that can't be solved using statistical models. Facial recognition is a good example. Now, I did an SVM facial recognition model, but in the real world, that's almost always done using deep learning. Any kind of hardcore image classification, like looking at a photo, identifying objects in it, telling you whether the photo has a dog in it or not, is almost exclusively the providence of neural networks. They're very good at that sort of problem. Statistical models are not. So I'll stop there. I could go on and on about the differences between statistical learning and deep learning, but we'll just have to do another webinar.
All right, a couple more questions. How do you approach unbalanced data sets?
Yeah, great question. So what if you are building a classification model, you look at your data set and find it's imbalanced? There's several ways you can address that. The most common solution is you throw away some of the data so that even though you're losing good data, you have more balance between the data you have left. In some cases, it is appropriate to reduce an imbalance by synthesizing data, and there are well-known algorithms for synthesizing it, but I would caution you there, because unless you really understand your data, really know what you're doing, you may be doing more harm than good by synthesizing the data. So the most common way we deal with imbalance is we throw away perfectly good data so that we have approximately the same number of samples of each different output class.
Okay, Gus says, I was wondering if you have looked at Intel's OpenVNO, unless I missed at VINO, and what your thoughts might be about that.
I have not. I've heard of it, but I haven't looked at it. So yeah, I better not render an opinion, because it would be an uninformed opinion.
Okay, one more question then. Brian wants to know, do you know a website where we can get some good data sets?
Yeah, website for good data sets. So one of the primary ones is kaggle.com, Kaggle. You have to, I think, register for a free membership to download most of the data sets, but they host a lot of really cool public data sets there. And they also hold competitions. So if you want to test your skills against other people who are learning, you can do that. In fact, I've been told that sometimes the winner of a competition will get hired by companies that are looking for those kinds of skills. Outside of Kaggle, there's several universities that maintain repositories of public data sets. One of the ones I look to from time to time is the University of California, Irvine. They call it the UCI data sets. You can do a search and find it. They have a lot of interesting data sets. One other source of data that we often rely on is US government websites. Departments of the government like the Department or the Bureau of Labor and Statistics and all make all sorts of data publicly available. Typically the data is not super clean. You may have to do some cleaning on it. You may have to pull down various data sets and combine them to get what you want. But there is a lot of good data available from the government if you do searches and go looking for it. So Kaggle.com, certain universities like University of California, Irvine, and government websites, probably the three most common places these data sets come from.
And that's it.
Great. Well, thank you for giving me your time. I hope it's been useful for you. If you're interested in doing machine learning with C#, I hope to see you back here in a couple of weeks for that webinar. And I'll work with Martha and Rachel and see if we can't get a deep learning webinar together soon, so that if you're interested in neural networks and deep learning and image recognition and all some of the real magic in ML, I'll show you how all that works. So have a great rest of the day, everyone, and I'll see you again soon. Thanks.